Good day, I'm Maile Matsiba. Welcome back to our channel. Today we are continuing with our CIR 211 module. We are looking at example 2.3.2.1. So this example comes from the CIR 211 study guide. It says 5 meter cubed of an air-water vapor mixture is at a temperature of 313 Kelvin and a pressure of 101.325 kilopascals. The partial pressure of water vapor in the mixture is 3.7 kilopascals. If the mixture is compressed to a final volume of 1 meter cubed and the temperature remains constant, determine the mass of water that will condense. It goes further to give information that the vapor pressure of water vapor at 40 degrees is 7.384 kilopascals, and also that the volume of the condensate is negligible. Now, for us to actually solve this question, I just need to do a few illustrations here. We have the first volume, which is 5 meter cubed, and in here we have like air, and we also have like H2O as in water vapor, right? And the total pressure here, and the total pressure is actually total pressure is actually 101.325 kilopascals, right? And the partial pressure of H2O, that is the water vapor, is equal to 3.7 kilopascals, and our temperature is actually 313 Kelvin. So now in here we have our water vapor and we also have the air, right? So and we have the information as far as the pressure and the temperature is concerned and the volume. So we are told here that the vapor pressure of water vapor at 40 degrees is 7.384 kilopascals. Now 313 is the 40 degrees. So now one important thing to know, remember we are being asked how much of water will condense. So the first thing we can actually do is to check if there is water if under these conditions actually there is water in this volume. And it's easy to check that because we simply compare the partial pressure of water and the vapor pressure of water. If the partial pressure of water is actually lower than the vapor pressure of water, then it means all of the water here is actually vapor. This is because the vapor pressure is actually the maximum amount of pressure that water vapor can actually handle at 40 degrees Celsius, right? And now we have a partial pressure of water vapor that is actually less than the maximum. So we are certain that under these conditions, there's no water here, it's only water. There's no water liquid, it's only water vapor, right? Now, an important thing we need to do here is to calculate. Remember, the question is they need to know. They say determine the mass of water that will condense, right? So the first thing that we can actually do is to actually calculate the amount of water vapor that is in here as far in kilomole, right? So we can just say number of moles H2O is equals to the pressure of H2O, which is the partial pressure of H2O, multiplied by the volume, right? We have two volumes, we can just say V1, right, all over R by T, isn't it? Now, when we do that, we know that the partial pressure of water is 3.7 kilopascals, right? Multiplied by our first volume is 5. Let me just ignore the units for now so that I don't have to. Yeah, so it's 3.7 kilopascals multiplied by 5 meter cubed, all over 8.314 multiplied by 313. Now, those number of moles, if you actually use your calculator there, so if you use your calculator, you'll find that the number of moles of water vapor there is 0.007110 kilomole. So that means the amount of water vapor here is actually 0.007110 kilomole. Now we are told that the mixture is actually compressed to a final volume of 1 meter cubed. So I can just put a smaller box here just for illustration purposes and say it's 1 meter cubed, right? Now we need to, okay, we still have air and we still have our H2O as in vapor. Now we are told that we need to calculate the amount of water that actually condensed. At this moment, even though we are asked this, it's important to understand that at this moment we can't really we can't really tell if there's water vapor, if there's actually water liquid in there, right? And which means that we're going to need to do a little test to actually verify if indeed there's water liquid here. And remember, we have our vapor pressure of water vapor, which is 7.384 kilopascals, which means the only other time where there will be water that has condensed in this 1 meter cubed volume is if reducing the volume from 5 meter cubed to 1 meter cubed while keeping the temperature constant has a capacity of raising the pressure beyond the vapor pressure, which is 7.384, right? Otherwise, there won't be water liquid there. So now how do we check if really this reduction of volume has a capacity of raising the pressure beyond the vapor pressure? There's a little test we can do. We can just say P1 V1 is equals to P2 V2. Let me just highlight here that this is the water vapor. Let me not interfere with this answer. This is the water vapor. Let me just say water vapor test, right? I like a better way of explaining that. And this pressure is the first pressure of water vapor, and the volume one is the first volume of water vapor, and the same with P2 V2. Now the first pressure of water vapor, we are told that is 3.7 kilopascals multiplied by the first volume is 5 meters cubed is equals to P2 is what we need, right? And V2 is 1 meter cubed, which means our P2 is equals to 3.7 multiplied by 5 all over 1. And if you actually use your calculator, it's gonna give you 18.5 kilopascals, right? Which means that, which if you look at it, is actually higher than the vapor pressure. And this tells us that actually water did condense here. Why? Because the principle of water vapor said, the principle of vapor pressure says that the vapor pressure is actually at a particular temperature, in this case 40 degrees. That vapor pressure is actually the highest amount of pressure that the water or whatever compound will be dealing with can be able to handle. Which means that reducing the volume from 5 meter cubed to 1 meter cubed by keeping the temperature constant actually has a capacity of raising the pressure to P2, right, to this value of 18.5 kilopascals. And because this value is actually higher than this, then it means that there is water here. It means that the water has condensed here. And I need to explain this, right? And this is because generally the reason why there's water here is that the water vapor at 40 degrees can never have a pressure of 7.38, a pressure more than 7.384 kilopascals, right? That is actually the partial pressure. So which means when the pressure attempts to go beyond 7.3 kilopascals, right, that water vapor then condenses the water just to make sure that it keeps the pressure or the partial pressure of water vapor right here. And that is the whole concept of vapor pressure, isn't it? So with that said, having done this test, we can tell that because this P2 is actually higher than this, then there is water here. Is it? Now, another important concept, now after we have established this, a very important concept or important question that we can actually ask. My camera seems to want to be blurry, Sorry about that. A very important concept, or rather, a very important concept that we need to discuss here is then if we have established that the P2 has a capacity of going beyond this, then what is actually the pressure of P1? And if this happens that water does condense here and reducing the volume actually has a capacity of taking it there, then our P2 by default becomes the vapor pressure. So our P2 is actually 7.384 kilopascals, which means in 1 meter cubed, our P2 then becomes our vapor pressure. Why? Because reducing the volume had a capacity of raising the pressure above the vapor pressure. But because of the principle of vapor pressure, scientifically we understand that when that happens, then the maximum pressure remains 7.84. And to maintain that and make up for this 18.5, then the water vapor then condenses part of the water vapor into liquid. I hope that is clear. And let's not forget that the temperature is still 313 Kelvin. Another question for curiosity purposes is that what if the temperature did not remain constant? The question will be a different story. So we'll have to use a different approach. But in this case, because the temperature is constant, then we can definitely be 100% sure that our P2 then becomes our vapor pressure, and we know already that there is water here, right? Now, let's not forget the question. The question says determine the mass of water that will condense, right? So, and now we can actually use our proofs. We know the amount of water vapor that was here, and we've already established that there was only all water vapor here. And secondly, we have the information that can actually help us calculate the amount of water in terms of water vapor here, right? Let me move this here. This is because, well, this is ideal conditions. When we have the temperature and the volume and the pressure, then we can actually calculate the amount of water vapor in kilomole that is actually in here. And we'll do just that. We can just say number of moles of H2O, right, is equals to, well, let me just say here that 1 meter cubed, right? Number of moles of H2O is equals to pressure H2O, right, multiplied by, this time we are using V2, right, all over R multiplied by T is equals to, what is the partial pressure of water in V2? We already established that it's actually the vapor pressure. So it becomes 7.384 multiplied by our V2 is 1 meter cubed. Let me not put the units. All over our R 8.314 multiplied by our temperature, which is 313, right? And if you use your calculator, then that is going to give you 0.0028375 kilomole. So now this becomes the amount of water vapor that is actually in 1 meter cubed. However, this does not account to the water that has actually become liquid here. And another important principle that I need to highlight here is that we are told that the volume of the condensate is negligible. Not really the condensate in itself, but the volume of it. Which means, remember, when it's only water vapor and air, then we have the whole volume. But when water condenses, that water actually takes part of the volume. And the issue is that if there really is too much water vapor that has actually condensed, it might end up, having to decrease the volume, and then that might affect our calculations. But we are getting an assurance that the volume of the condensate is negligible. We can actually do without. We can actually not really worry about it, right? But that does not mean that we are not calculating the condensate. It's just that the volume does not really interfere with our calculations. So now we have two important information here. We have the number of moles total of the water vapor initially, and we also have the number of moles of water vapor later after it was compressed. So which means that we can actually say, okay, if this was the total water vapor, so if this was the total amount of water vapor, then we can use the difference and say this total amount of water vapor in kilomole is actually equals to the total amount of water vapor here plus the liquid, isn't it? So with that said, we can just say, let me just write here and say water condensed is equals to, right, number of, how do I want to put this in a, let me say water condensed in kilomole is equals to the total amount or the initial amount of water vapor that was here, which was 0.007110 kilomole, right, minus the water vapor that was there, which is then we calculated to be 0.0028375 kilomole, right? And if you use your calculator, then we can know that the amount, the kilomole, the water that was condensed in kilomole, then is equals to 0.0042725 kilomole. So now this is actually the amount of water that actually condensed, but it's in kilomole. And they say they want the mass. Let me bring the question again. The question said they want the mass of water vapor, rather the mass of water that is actually condensed. Yeah, this is the question. It says that they say determine the mass of water that will condense, right? So now with that said, that means that we actually need to calculate the mass from the kilomole, which is not so difficult. So we can just use our, we can actually just use our traditional conventional or old way of calculating our mass. We know that number of moles is equals to mass all over molar mass, right? Therefore, mass of H2O condensed, right, is equals to number of moles multiplied by molar mass, isn't it? And that equals to our number of moles. We've already calculated it to be 0.00422725, 0.004725 kilomole, right, multiplied by the molar mass of water is 18 kilograms per kilomole, right? And if you use your calculator, it's gonna give you 0.076905 kilograms. So now if we have reached here, then we have answered the question, and yeah, we have solved the question. So thank you guys for your time, and I hope we meet again in our next video. So yeah, this is actually our final answer.